Good evening, I'm Anas Tiwari, and today I'll be talking about computation of modular inverse in cryptography for my second digital assignment of cybersecurity. So, to start with, let's talk about what is modulo inverse. Now, I won't be stressing a lot on something that we have already learned in cybersecurity. So, modulo inverse is, uh, say, 1 mod p. So, technically, modulo inverse is the value which when multiplied with a number gives 1 modulo a mod, which is basically a prime, or it can be anything. So, putting it here, the number x is the modulo inverse of a under p. So, something like this. Right. Now, even the computation of modulo inverse is not very hard as we have studied in the course. So, modulo inverse is computed using extended Euclidean theorem uh, when we try to do it by hand. So, I won't be stressing over it, but it is usually done with extended Euclidean theorem. But computers don't use it. Computers don't use extended Euclidean theorem due to some security issues. Plus, it is computationally little complex to implement. So today I'll be talking about a new way to calculate modulo inverse in computers, and which is very widely used in cryptography as well as in a lot of hashing techniques. So this comes from, and I'll be showing code on how to really calculate it and how the computers do it. So this comes from a well-known algorithm, or what we can call a mathematical equality. That's Fermat's theorem. So what Fermat's theorem suggests is, given a prime number p, this holds. Right, a raised to the power p, and if you take the mod of it under p itself, you get a. Now, it can be seen that this can be very easily extended as a raised to the power p, a mod p. Now, even this extension is very popular, where you have to multiply a inverse on both sides. So what you get is a raised to the power p minus 1 is 1 mod p. Right. Now if you try to do this again, you'll get a raised to the power p minus 2 is the modulo inverse of a under p. Right. So essentially saying that if say p is a prime and you calculate the power of a number to the same mod minus 2, and of course you take it under the mods, so mod p, this is basically a inverse or modulo inverse of a. Right, this will give you a inverse under p. Right, straight and simple, and this can be derived from Fermat's theorem as we talked about it earlier. Again, I just want to stress on it that yes, you can use extended Euclidean theorem to calculate this, but that is usually when you do it by hand. And for cryptographic purposes, extended Euclidean theorem is not as secure as using this Fermat theorem to calculate modulo inverse. Okay, now you might say that calculating this will be too heavy on computation, right? Because again, I won't go in the proving that an extended Euclidean theorem works in the time complexity of O of log of max of A and B, A and P, right? And calculating something with the power of this big will straight on the O of P, right? And of course, this seems to be lot less efficient than extended Euclidean theorem. Right. So, right? So why do computers use this? Now, here I'm going to introduce another concept using which you can calculate the power not in O of p but in O log of p. Right, and this is what computers make use of a lot. So that is called binary exponentiation. It's called binary exponentiation, where you can calculate some number to the power some number in logarithm of the power time complexity. So O log of p. This is time complexity. Now, if you, I'll prove the time complexity soon. And if you see that it's as close to this because maximum of a comma p will mostly be p, right? Because if you are trying to calculate uh, a a p and under the mod, so automatically a will be written as a mod p comma p, and the maximum of these is of course p. So again, this is exactly O log of p as we are trying to do here. So we are not getting any worse time complexity, and plus binary exponentiation and technically calculating mod inverse using this Fermat's theorem is a lot more safer than doing it using extended Euclidean theorem. And computationally, it's easier to implement as well, which we'll be seeing later. Alright, so what is binary exponentiation? So say you need to calculate some number to the power something, say 2 raised to the power 16. So instead of multiplying 16 times, what you can do is you can calculate 4 raised to the power 8, this whole raised to the power 2. Meaning you can calculate this and you can multiply it twice within itself, right? So if you can capitalize on this, why stop here? So we can again break it down into 16, 4, or we can do actually better, and two raised to the power 16 can be written as 2 raised to the power 2 raised to the power 8, that is 2 raised to the power 2 to 4, and you can keep on doing this and you will get something like this, right? So essentially saying, after you calculate this, you multiply it with itself, then after calculating this, you multiply it with itself, then after calculating the whole of this, you multiply it with itself. So basically you're making, for 16 power, you're making 4 multiplications, right? So 4 iterations, that is equal to log base 2 of 16, right? So this is how you get this. Right. So what this helps us is, say mod is a very big number, and you might have seen this number lot of places. That's 1e9 plus 7. So basically, this is the not the largest, but this is very familiar 32-bit stored prime number, a large prime. So this is 10 raised to the power 9 plus 7. So say calculating a raised to the power this number will take 1e9 plus say you are calculating in layman terms using brute force. So O of this, O of mod, this is something close to like 10 minutes or something. And doing same O log of mod, this is log of mod will be something like for the relative bit will be O of 32, that is like instantly like 1 millisecond, something like even less than that. So the computation difference is huge just by using binary exponentiation. Alright, so this is what the theory part. Now I'll try to explain how we do this using code, and let's try to solve some examples. So maybe we can solve some examples here itself, and we can go and verify it in the code using both of those. So 2 inverse mod 5. So if you calculate this, it should be 3, right? 3, 6 mod 5, right? And we'll actually generate other examples there itself. Now, okay, now let's look at the binary exponentiation part first. So this is how you start. This computes a power of a to the power b. So let's show an example. So 10 raised to the power 2. Right. So I'm using C++ to do this. So 10 raised to the power 2 gives us 100. So if you see, this is a raised to the power b again. So I'll just break down the code. So result is what you will be returning. And what happens is, now we talked about like how do you compute like 4 raised to the power 5, right? So you can break this down into 4 raised to the power 2 into 4 raised to the power 2 into 4, right? So this is essentially 4 raised to the power 4 raised to the power 2 into 2. So wherever you get an odd number, for whatever power, you multiply that to the answer. So for computing this, what you will do is, you will calculate 4 into 4 raised to the power 4, right? And for even powers, it can always be broken down into 2 powers, right? So 4 raised to the power 4 can be broken down into 4 raised to the power 2 raised to the power 2, right? Similarly, if say there is a power 8 raised to the power of 11. So when you try to break this down, you can break it down into 8 into 8 raised to the power 5 raised to the power 2, right? And again, 5, even 5 is an odd number. So you'll do, for this, you'll do 8 raised to the power 8 raised to the power 5 2. So to calculate, this 2 goes here. Now you'll again do 8 into 8 raised to the power 2 raised to the power 2, right? So this just comes out and it becomes 8 raised to the power 11. If you see, this 8 gives you 10 and this is 1 power, right? So wherever you are getting an odd number, power, you multiply the same number to whatever result you are again recursing within. So I'll show you the code, then it will be easy to understand. Okay, now you see here. So while b suggests that while b is greater than 0, so C++ treats any 0 or negative number as a false condition, right? So this breaks when b goes to 0 or goes less than that. It will always go to 0 anyway. Now take care of this multiply function. So multiply function is nothing but you are just multiplying two numbers under the mods, right? So that you do not cross the threshold, and if you are somehow multiplying a negative number, you add mod to it, right? So that will still be under the mods, because say if res is less than 0, right, but it's greater than minus of mod, right? So res plus mod, now you can just add mod to both sides of the inequality and it will become res plus mod is greater than 0, so we brought it to a positive domain, plus it's less than mod as well, right? Alright, so that was for multiplication. And again, if it is a odd number, if power is odd number as we talked about, you multiply the result with the current a that you are working on, or the current base that you are working on, right, as we did here. So 8 raised to the power 11, 11 is an odd number, so you multiply 8 to the answer here, right? So res is basically the answer, and for a, you multiply it again with itself, right? So this thing that we're talking about, you multiply it again with itself. So actually I'm explaining it top down. Now I'll explain about how code works here itself, right? Now again we'll try to do 8 raised to the power 11 here. right? And this will be done under the modes, remember that. So it won't cross mod. So let's try to derive on it. So res is 1. Let me see if I can get this there. 8 raised to the power 11. Next. Yeah. Okay, we are trying to compute 8 raised to the power 11. Right, and so our A is 8, B is 11. So initially res is 1. Okay, now while B is 11, okay, because B is an odd number, res gets multiplied by A, which for A is initially 8, right? So res is 8 to multiply res by 8. Now B, A is also multiplied by A itself, so A becomes 8 raised to the power 2 here. I am breaking down just for simplicity. Now you divide B by 2, so this is an integer division, so 11 will become 5 and not 5.5, we'll lose the decimal part. Now B is again odd, so you multiply res by A. Now remember that A right now is 8 square, so this becomes 8 raised to the power 3, right? Now again you multiply A by A itself, so A becomes 8 raised to the power 4, so 8 square into 8 square is 8 raised to the power 4. B becomes integer division becomes 2, right? Now when B is 2 and B is a positive number and it's not odd, so res becomes what it is right now, so it is 8 cube. Now A, just remember that A is always being multiplied by itself, so A becomes 8 raised to the power 8 now, and B is 1, which is an odd number, so res is multiplied by A, so that is 8 cube into 8 raised to the power 8, that is 8 raised to the power 11. And again after B you do B by equal to 2, B becomes 0, and you come out of the loop, right? And what you return, it is the result. And if you can see, it is 8 raised to the power 11, right? And how many iterations we took? We just took 4 iterations, right? So 4 here is log of B, which is the power, which was 11. So log of 11, it's something, it's more than 3 point something. It should be 3 point something. So basically you took 4 iterations, so you can generally take it as C, or whatever log, you remove the decimal part and go plus 1, right? So basically it's close to log, right? So this is how binary exponentiation works, right? Now after binary exponentiation is done, you can always do A to the power mod minus 1, mod minus 2 to get the inverse, right? This is basically A inverse mod of whatever mod you took, right? Now we'll try to do this also. Okay, let's first try a few examples, right? So let's see what is 2 raised to the power 10, should be 1024. Yes, it's 1024. And okay, actually we can prove whatever we did here by printing A, or let me just do a debug A, B, res, right, for all steps, for 8 raised to the power 11. Now of course this won't print that in powers, but if you can see, A is initially okay, before starting, let me print this again. So before starting it was A 11 and res was 1. Now this became 8 square and res became 5, power became 5, res became 8, right? Exactly how we were discussing here, right? And then this became 8 square, power became by 2, res 8. This got squared again, so this is like 64 square, this is 5 by 2, right? And this is multiplied by 64, 8 into 64. Now this is 4096 square under the modes. This is 2 by 2 is 1, and because this was even, we didn't multiply it by A, so this is 5.2. Now as this became odd, we again multiplied it by the current A that we had, and this became this, right? And essentially A became this and this became 0. So after this becomes 0, we are returning this as the answer. So this is what we are getting here, right? Similarly, something like 2 raised to the power 20. As you can see, the number of iterations are pretty low. Like 2 raised to the power 20, you just completed it in 6 iterations, right? Now, what I wanted to show you was, let's say, we come back again to mod. So I'll take a mod that's huge, and this is the whole point of binary exponentiation. So it's 29 plus 7, right? And now I'll do 2 raised to the power 29 plus 7, right? And I hope it's accepted. Yes. Now you can see the amount of debug happening. It's of course not 29 plus 7. It's a lot less. It's something close to 30, 32, right? And we are putting 2 raised to the power 29 plus 7. Right. Now similarly, I'll show you how to compute inverse mod. So mod is 5 and 2 raised to the power mod minus 2, this should be, and we'll print it into the mods. So this should be 3, right? 2 into 3 is 6, 6.5 is 1. Similarly, you can calculate anything. Say, like even you can calculate this for 29 plus 7, right? So 504. If you twice it, it becomes 29 plus 8, which modulo this gives 1. Now, it is irrespective of what A is, because mod is always prime. We are taking prime mod, and even Fermat theorem suggests us to take prime numbers for mod. So even if you take a very big number here, say 1, 2, something, pretty big number, right? Anyway, it's inverse is calculated real quick with binary exponentiation, right? And applying all the modular arithmetic. So that was it, and this is how computers in cryptography calculate modulo inverse, and they don't really use extended Euclidean theorem for calculating it. So that was the TA. Thank you.